Okay, today we discuss about polarizations. Okay, uh, polarization is a electromagnetic properties. Okay, the concept of the polarizations is basically this is describe the orientation of electric field in direction of the propagation with respect to time. That the properties of the electromagnetic wave describing the time varying direction and relative magnitude of the electric field vector. Okay, especially the figure traced as a function of time by the extremity of the vector at a fixed location in the space and the sense in which it is traced and observed along the direction of propagation. So there are the two figures. First, rotation of the wave, other is polarization ellipse. Basically, the electric field component x and y are perpendicular to the direction of propagation. And second thing is represent the ellipse. Okay, ellipse, they are the two axis, major axis and minor axis, and this is the E component of the electric field component in the x directions, or other thing is electric field component in y directions. Okay, now we discuss the linear polarization, circular polarization and elliptical polarization. Okay, before first we studies the instantaneous field of the plane wave. Okay, the direction of the plane wave propagation is negative z directions. So we can write the electric field component. Electric field component, combination of electric field component of x direction and component of y direction in term of z and t. Now we represent the electric field component x component in term of the complex format. Okay, so it is the real part of the electric field component in x direction, x e x naught e wt kz phi x, where k is constant and phi x means constant phase difference, phase angle for x component. So we can write in sinusoidal form ex naught cos wt plus kz plus phi x. Second thing, we can write the similar y component e y naught cos omega t plus kz plus phi y. Okay, where ex naught and ey naught are maximum magnitude of x and y component. Okay, the concept of the linear polarizations. Okay, basically their concept, the phase difference between x and y equal to n multiple of pi, n 0 1 2 3 and so on. Okay, the concept of the circular polarization, there are the two properties. One property is the magnitude of the electric field and electric field in x direction and magnitude of electric field in y directions are equals. Second property is the phase difference between the ex and ey, electric field in x direction and y direction, plus 1 by 2 plus 2n and multiply n multiply pi n 0 1 2 3 for clockwise directions. Similar for negative signs for counterclockwise directions. Okay, basically If the direction of the wave is reverse, that is in positive direction, in this case we consider the negative direction. But if the direction is consider the proportion of direction is positive direction, then the phases in the for the continuous clockwise direction and counterclockwise direction rotations must be interchanged. Okay. Second thing, elliptical polarizations. The properties of elliptical polarizations are the magnitude of electric field in x direction and magnitude of electric field in y directions not equal, but phase difference properties similar to the circular polarizations. Okay, positive 1 by 2 2n multiply pi for clockwise polarizations, and second thing for negative signs for counterclockwise polarizations. Okay, now the axial ratio, how we can define the axial ratio? Basically axial ratio is ratio of the major axis to the minor axis. Okay, in this polarization ellipse you can see this is the major axis or this is the minor axis. This is the x component of electric field, this is the y component of the electric field. Okay, so the range of the axial coefficient 1 to infinity, if the axial ratio equal to 1, if the axial ratio equal to 1 means the minor axis equal to the major axis. In this case the ellipse is look like the circular. Okay, so this is the circular polarizations. If the axial ratio is greater than 1, then it convert into the elliptical polarizations. Okay, and other thing, high at infinite or 0, the polarization is linear polarizations. Okay, basically the polarization is useful for the antenna alignments, basically for application of satellite communications. You have point to point communications, they need polarized antennas. In case of satellite communications we need generally the circular polarizations. Okay, or for point to point communications we need vertically or horizontal polarizations. Okay, so they are the properties for polarizations generally used for the antenna and other electromagnetic components. Okay, in radar section also we can use the polarization concept. Okay, now we discuss about input impedance of the antenna. Okay, so what is the input impedance of the antenna? Basically this is the ratio of the voltage to current at terminal A and B. You can see input impedance of the antenna basically the ratio of the voltage to current at terminal A and B. Okay, so you can see in case of no load attached, the input impedance ZA antenna input impedance, RA antenna resistance input resistance, and ZXA antenna reactance. Okay, this is the antenna structures and this is the transmission lines with generator. This is generator connected by transmission line to the antenna terminal A and B. Okay, and this is a radiated electromagnetic waves. So now it convert into the Thevenin's equivalents. So you can see this is the VG voltage, generator voltage, resistance, generator voltage generator resistance and generator reactance. Or after the terminal AB, RL, this is the loss resistance of the antenna. R, small r, this is the radiation resistance of the antenna. Or XA, this is the reactance of the antenna. Okay. So total resistance of the antenna is Ra equal to loss resistance and radiation resistance. Okay. And total in generator impedance is Zg equal to Rg plus Jxg. Okay, so we first find the current developed within the loop, which is given by in Thevenin's theorem. Okay, so current Ig equal to total voltage upon total impedance. What is total voltage is equal to? In this loop, total voltage is Vg, and total resistance, total impedance Zg, Za plus Zg. So in Za, Ra, Rl, Rg, and Zg, Ra, Xa, Xg. Okay. So it converted in magnitude form. So we square the in imaginary part in term, then you can see this. Okay. Vg is the peak generator voltage. The power delivered to the antenna for radiation is given by basically the power delivered for antenna for radiation purpose. So PR 1 by 2 Ic square multiply R small r. Basically this is the radiation resistance. So this power represents the power delivered for the radiation purpose. Okay. So we can write these equations. And second thing is dissipated as heat. Okay, by heat, the antenna is power dissipated by the heat. The resistance would be loss resistance. Basically the resistance is loss resistance. So this power is dissipated as a heat. Second thing, the remaining power is dissipated as a heat on the internal resistance Rg of the generator. So the power dissipated by the generator is given by the generator resistance. Okay. The concept of the maximum power transmissions. Okay. So the real part of the resistance of generator equal to the total resistance of the load. In this case, the load is antenna. The total antenna resistance is RL plus RL. Okay, or Rg equal to generator resistance. Similarly, maximum power transmission concept, the real part equal to the basically the reactance of the generator is negative of the reactance of the load. So this is the antenna reactance, and this is the minus Xg is generator reactance. So we apply this equation in the previous three power equations. So we can calculate. This is the final equations for the first is power distribution, power transmission for the radiations, power distribution by the resistance, internal resistance, or power distribution by the internal resistance of the generator. Okay, this is the concept of the input impedance of the antenna. Okay.